Today we're going to deep dive into the kind of thing you can only invest time on if you're a single engineer working on a project with no supervision. I just completed a crazy complicated development effort in my project testtrim, and all I want to do is talk about how surprised I am that it actually worked. First, let me give you a bit of context. Testtrim is an experimental project to optimize execution of software tests. It works by running your tests once and then analyzing test dependencies through code coverage and syscall tracing. Then, when any future software changes occur, it can use that analysis to minimize the tests that need to be run again. I went into more detail on the code coverage side in an earlier video, but today we're going to talk about syscall tracing. There are two types of dependencies that I want testtrim to find that require syscall tracing: reading files that are part of the repository and accessing resources over the network. If a test does either of those things, it requires some special handling to determine when the test needs to be run again. For example, if this file changes in the future, it would make a lot of sense to run this test. The tool that I always reach for when I need to do syscall tracing is called strace. You take a command that you want to run and you throw strace at the beginning, and you get a record of all the syscalls that the command made. It took a couple of weeks to develop the first draft of syscall tracing in testtrim using strace. It was pretty straightforward engineering. There wasn't a lot of complicated elements to it. When you run testtrim from the command line, testtrim finds all of the tests in your project, and then for each test, in parallel, it runs the test under strace. When the test process, here process ID 1234 or PID 1234, performs a syscall like opening the file fixture.txt, strace writes a record to the output file. When the test is completed, testtrim reads the data file and parses it, and then you can interpret the syscalls into dependencies that are part of that test. Like in this case, that test case requires fixture.txt. If that file is part of the repo of that project, then it will become a dependency. And if it's changed, then testtrim knows that test case needs to be rerun. But here's the catch. I want to use testtrim to test testtrim. The best way to iron out problems in software is to use it. Testtrim has integration tests which use miniature test projects to verify that testtrim works. The problem is you can't use strace on a process that is already being traced. Honestly, understanding the roadblock that this posed was a really disappointing moment for me. Syscall tracing worked. My miniature test project showed that, and there was apparently nothing blocking me from using it on other projects. But it was always a goal of mine for testtrim to work on itself. This would allow me to work out kinks and bugs, to generate the data set that would prove its own value in test target reduction, and to not be a hypocrite trying to promote something that I didn't even use myself. This was a problem that had to be solved. After a bit of disappointment, I had a light bulb moment. I control both of these programs. Can I just make them cooperate? The tracer, testtrim, knows everything that all these processes are doing. It's just a simple matter of getting the data from over here in the test application to over here in testtrim. So first pass, this turned out to be a little bit naive. I injected an environment variable into the test process, into the child that contained the path to the strace output file that testtrim was currently writing to. The child's job was simple: spawn the test process without any tracing, and then once the test is complete, read the strace output file that the parent provided. It needs to filter out to just the process IDs that are relevant to the test process, but that's pretty straightforward. This does somewhat work. It provides the knowledge that the test case requires fixture.txt to the subprocess, and over here in testtrim, it can identify that the integration test requires, called rust check in this case, requires whatever else it finds from the syscalls. But if you can see the problem with this approach, then you are very, very clever. I did not until I ran into it. You see, every time the child goes to read data from the strace output file, it has to perform a read syscall, which then goes back to the parent's strace, which then gets written to the output file, which then the child has to read. Well, that loop seems kind of infinite. Well, It's not quite infinite because there is an exit condition. The child process, the integration test, can stop once it identifies that the test it's running has terminated. So for example, if the test was process 4321, the integration test, which is process 1234, can stop once it hits the exit condition and notices that process 4321 has exited. It's not an infinite loop, but there is an incredible magnification going on of syscalls. Every syscall in one process causes another write to a file, which causes more syscalls within the same process. The performance of the solution was very, very bad. The more tests that needed to be run in a subprocess, then the more times it was rereading the syscall data, which included every syscall involved in its last reread of the syscall data. When combined with multiple parallel tests running, there's a geometric growth in strace output that needs to be read. So I came up with an alternative that seemed far more promising for a little while. strace has an option called -- output separately. This changes the output location to a file prefix rather than a file, and it outputs each process that was traced into its own file with that prefix. This seemed to work for testtrim's needs pretty wonderfully. Using -- output separately, we could write one file per process, pass the location of the files to the child process. When the test process completes, the integration test can just read the child's PID file. No more syscall amplification, magnification. There is, of course, a complication. It seems small, and then it becomes really messy. We can't just read the file with the child's PID. We also need to read any subprocesses of that process and any subprocesses of those processes. The simple solution is that we read the child's PID file, notice any processes that were spawned by that PID, and then read those files as well, and repeat the process until we've read all of the necessary files. Well, the problem is that processes aren't independent. Usually you'd use the word process to refer to a program execution which is operating independently, and thread to refer to multiple concurrent executions within a single process. In strace's output, it's outputting each thread to a separate output file as if they were processes, but they have shared state that is relevant to our syscall tracing. To keep things simple, we'll use the current working directory as an example. Let's say that process 4321 and 4322 are both threads. If PID 4322 changes the current working directory and PID 4321 opens a file with a relative path, in order to know what file was opened, we need to know the order that these syscalls occurred in. But we started sending this data to separate files, and we don't know the order of these events anymore. I took a brief look at using strace's timing outputs in order to provide ordering, but first it seems sketchy in terms of accuracy, and second, the performance of strace gets much, much worse. It needs to constantly access the system clock, so that performance drop makes sense. Getting to a solution that met all of the criteria required one simple tweak and one complicated tweak. First, I reverted to the single output stream rather than using -- output separately. Other than timestamps, this was the only way I was going to get an ordered view of the syscalls between different processes. The simple tweak was to start to stream the data from strace into the parent process through a FIFO pipe, which allowed the parent process to parse and understand the data asynchronously while waiting for the subprocess to finish. Now that the data was live and active and available in the parent process, I just needed to get access to that event stream from the child process without using one syscall per syscall I wanted to read. So the complicated tweak was to communicate data between the two processes without triggering more syscall amplification. Ignoring some of the finer engineering details, the architecture ends up looking like this. The testtrim process opens a Unix socket and passes the address of that socket down to subprocesses through an environment variable. When a test wants to start a test case with nested tracing, it connects to the testtrim process through that Unix socket, and it sends a request to subscribe to the process ID of the child process. Testtrim starts a shared memory buffer and begins to store any syscalls from the process ID of the child. This is where the live connection through the pipe to strace matters. we're able to instantly connect to that data stream and copy it into that shared memory buffer. Testtrim sends back to the test process an address for the shared memory buffer. And then on an ongoing basis, testtrim writes syscall data to the shared buffer, and the test process reads it out. A ring buffer is used so we can have a fixed memory allocation, which supports a continuous stream of data between the two processes, written by the testtrim process, which is running the strace, and read by the integration test, which wants the syscall data. Does this work? Yes. It took more than a few passes to get the synchronization logic correct, and with this complexity, there might still be a surprise or two to learn, but it functions. With this design, nested strace data collection is impossible, and the order of syscalls is preserved such that we can recognize dependencies between threads, like changing the working directory of one thread and then opening a file on another thread. This has been the final piece in the puzzle to getting testtrim to be able to run on its own project in its own CI. It's a shame that the nested logic will never be useful for anything else, but I think it's pretty cool anyways. There's one more neat thing that testtrim is doing with syscall tracing, which is more generally applicable to other test projects, but that seems like a topic for another video. Until then, I hope you've enjoyed this deep dive.